Right now, you believe that the Andromeda Galaxy sits roughly 2.5 million light-years from where you are. You believe the closest star is about 4 light-years away. You believe that distance in space is real, measurable, and absolute. But what if every single measurement of cosmic distance you have ever encountered is fundamentally wrong? What if distance itself is not a basic property of reality, but rather a trick your brain performs on you? What if, at the deepest level of physics, space contains no distances whatsoever? What you are about to encounter will permanently reshape your understanding of what space actually is. Distance feels like the most self-evident thing in the universe. You are sitting some measurable gap away from the screen in front of you. The moon is roughly 250,000 miles away. The sun sits approximately 93 million miles from Earth. These separations feel real, fixed, and permanent. Distance seems like nothing more than how far apart two things happen to be. It appears to be the simplest concept in all of physics. But simplicity is frequently the disguise that the deepest mysteries choose to wear. Distance, the most seemingly obvious property of space, turns out to be one of the most profoundly misunderstood ideas in all of science. It is not fundamental. It is not absolute. It is not even real in the way your intuition insists it is. And the journey toward understanding why will carry you through quantum mechanics, general relativity, holography, and the very foundations of what space itself actually consists of. Let us begin with something you might think you already understand: the speed of light and what it reveals about distance. When astronomers state that the Andromeda Galaxy is 2.5 million light-years away, they are making a claim that sounds like a distance measurement but is, in truth, a time measurement. A light-year is simply the distance that light covers in 1 year. Saying something is 2.5 million light-years away means that light requires 2.5 million years to travel from that location to here. But here is the difficulty. You are not measuring where Andromeda is at this moment. You are measuring where it was 2.5 million years ago, when that light was first emitted. By the time that light reaches your telescope, Andromeda has moved on. It has been in motion for 2.5 million years. The distance you measure is a distance to a ghost, to where Andromeda existed millions of years in the past, not where it actually resides right now. And because the universe has been expanding throughout the 2.5 million years that light was in transit, the actual current distance to Andromeda differs from the distance the light traveled to reach you. Space itself stretched during that journey. The distance the light covered is therefore not identical to the present-day separation between you and Andromeda. Every cosmological distance measurement blends at least 3 separate distance concepts: the distance light traveled, the distance at the moment of emission, and the current distance accounting for cosmic expansion. These are all distinct numbers. Which one represents the real distance? The honest answer is that none of them is more real than the others. They are all legitimate measures of separation depending on what question you are posing and which reference frame you are working within. There is no single definitive fact about how far away a distant galaxy truly is. Distance at cosmological scales is observer-dependent and definition-dependent. It is not an absolute truth about the fabric of reality. But this is only the beginning. Special relativity dismantles the absoluteness of distance far more aggressively. In 1905, Albert Einstein demonstrated that distance is relative, not approximately relative, not loosely relative, but absolutely, fundamentally, and mathematically relative in a way that depends entirely on how fast you happen to be moving. Here is the essential result. A ruler moving past you at high speed is physically shorter than an identical ruler sitting at rest. Not because something is pressing on it, not because it has been mechanically compressed, but because the geometry of spacetime is structured such that a moving object occupies less extent in its direction of motion than the same object would at rest. This phenomenon is called length contraction, and it is a real, measured, experimentally verified fact of nature. At 10% of the speed of light, an object contracts by roughly 0.5% in its direction of travel. Small, but detectable. At 90% of light's speed, it contracts to approximately 44% of its resting length. At 99% of light speed, it shrinks to around 14%. As velocity approaches the speed of light, length approaches zero. What does this imply for cosmic distances? It means that distance is entirely frame-dependent. If you were aboard a spacecraft traveling toward Andromeda at 99% of the speed of light, the distance between you and that galaxy would not be 2.5 million light-years. It would be 2.5 million light-years divided by the Lorentz factor, which at that velocity yields a distance of roughly 350,000 light-years. You and someone standing still on Earth would record completely different distances to the same galaxy. Both measurements are entirely correct within their respective reference frames. There is no privileged absolute distance. At the speed of light itself, the contracted distance would reach zero from a photon's perspective, if such a perspective were meaningful, which it is not. The distance from a photon's point of origin to its destination is exactly zero. Every cosmic distance is zero from the reference frame of light. The entire observable universe has no size whatsoever from the standpoint of light itself. Distance in space is already not absolute. It shifts with your speed. It shifts with your reference frame. Different observers record different distances between the same 2 points, and every one of those measurements is equally valid. There is no objective truth about the actual distance between 2 points in space that exists independently of who is doing the measuring and how they are moving. But even this is not the deepest level at which distance collapses. General relativity goes further still. In general relativity, space itself is curved. Mass and energy warp the geometry of spacetime. Near a sufficiently massive object, space curves dramatically. This means that the separation between 2 points is not set by some fixed background geometry. It is determined by the distribution of matter and energy in and around that region. Near a black hole, space curves so severely that the distance from outside the event horizon to the singularity within is effectively infinite, even though the black hole has a finite radius as measured from the exterior. An observer falling into a black hole experiences the interior as having an enormous volume, far larger than the black hole appears from the outside. The interior of a black hole contains vast amounts of space that are simply inaccessible from the outside. This demonstrates that distance is not a fixed property of space. It is determined by geometry, and geometry is determined by matter and energy. Alter the distribution of matter and energy, and you alter every distance in the universe. Distance is not a passive backdrop against which physical events unfold. It is itself a physical quantity that changes in response to the physical configuration of the cosmos. Curved space also means that the shortest path between 2 points is no longer a straight line. In curved spacetime, shortest paths are called geodesics, and they follow the curvature of space. The length of a geodesic depends on the curvature, and the curvature depends on the mass and energy distribution. 2 points that appear close together in flat space might be separated by a vast geodesic distance if a massive object lies between them, or might appear to be nearby because gravitational lensing bends light around that object. Even the idea of 2 points occupying the same location becomes strange inside a black hole due to extreme spacetime curvature. 2 points that share the same spatial coordinates in one coordinate system can occupy vastly different positions in another. The coordinates we use to label points in spacetime are entirely arbitrary. Different coordinate choices produce completely different accounts of which points are near each other, and which are far apart. This is not a mere mathematical formality. Physical effects depend on coordinate choice. What appears as a powerful gravitational field in one coordinate system looks like flat, empty space in another. What registers as an enormous distance in one system can appear as a tiny separation in another. The coordinate invariant truths about spacetime concern its geometry and topology, not simple distances between points. Now we arrive at the deepest and most radical way in which distance in space is revealed to be an illusion. Quantum entanglement and the holographic principle. Quantum entanglement is perhaps the strangest phenomenon in the entire body of physics. When two particles interact and become entangled, they form a single quantum system described by one wave function, regardless of how far apart they are subsequently moved. Measure a property of one particle and you instantly know the corresponding property of the other, no matter how great the separation between them. Albert Einstein called this spooky action at a distance, and devoted considerable effort to demonstrating that it was impossible. He was wrong. Entanglement has been confirmed in thousands of independent experiments. Two entangled particles can be situated on opposite sides of the observable universe and still constitute a single quantum system. Spatial separation does not dissolve entanglement. Distance does not diminish it. Two entangled particles separated by billions of light-years are quantum mechanically closer to each other than two unentangled particles that are physically touching. This exposes something profound. Quantum mechanical proximity and spatial proximity are entirely different things. Two particles can be spatially remote but quantum mechanically unified. Two particles can be spatially adjacent but quantum mechanically independent. Spatial distance does not capture what is genuinely happening at the level of quantum reality. Physicist Juan Meldacena made one of the most revolutionary discoveries in the history of theoretical physics. In 1997, he identified a precise mathematical equivalence known as the ADS/CFT correspondence between a theory of gravity operating in a particular curved spacetime and a quantum field theory with no gravity living on the boundary of that spacetime. The gravity theory inhabits a space with one more dimension than the boundary quantum theory. Yet the two descriptions are entirely equivalent. Every observable in one theory translates precisely into an observable in the other. They describe exactly the same physical reality from two utterly different vantage points. This is the holographic principle in its most rigorous mathematical form. The physical reality we experience in 3 dimensions of space can be completely and exactly described by a theory living on the 2-dimensional boundary of that space. The third dimension of depth, the dimension that generates our sense of distance and spatial extension, is not fundamental. It is emergent. It arises from the quantum entanglement structure of the boundary theory. Consider what this means for distance. In the 3-dimensional bulk theory, distances exist. Things are close or far apart. Gravitational effects depend on separation. The geometry of spacetime governs distances. All of this appears fundamental and real. But in the 2-dimensional boundary theory, there is no bulk distance. The boundary theory has its own 2-dimensional geometry with its own distances. But the 3-dimensional depth, the distance extending into the bulk, is not a geometric distance in the boundary theory at all. It corresponds to something entirely different. Specifically, it corresponds to the energy scale of the boundary theory. High-energy processes in the boundary theory correspond to small distances from the boundary in the bulk. Low-energy processes correspond to large distances from the boundary. What we perceive as distance in the 3rd dimension of space is actually energy scale. In the underlying quantum theory, distance is not fundamental. It is a way of characterizing quantum mechanical relationships between degrees of freedom operating at different energy scales. Depth in space is an emergent property arising from the structure of quantum entanglement in the boundary theory. This is not an approximation or an analogy. It is an exact mathematical equivalence demonstrated to extraordinary precision. Space, specifically the radial distance dimension in the holographic framework, literally emerges from quantum entanglement. Recent work by physicists Mark van Ramsdonk, Brian Swingle, and their collaborators has made this connection even more explicit. They demonstrated that the geometry of spacetime, including all its distances and curvatures, is determined by the entanglement structure of the underlying quantum fields. A concept called entanglement entropy, which measures the degree to which different regions of a quantum system are quantum mechanically entangled, determines the geometry of the corresponding spacetime. Regions of spacetime that are close together correspond to strongly entangled regions in the quantum description. Regions of spacetime that are far apart correspond to weakly entangled regions. Distance in space is entanglement in quantum mechanics. These are 2 descriptions of the same underlying reality. Van Ramsdonk illustrated this with a compelling thought experiment. Take the quantum state of the boundary theory and reduce the entanglement between 2 halves of it. What happens to the bulk spacetime? The bulk spacetime tears into 2 disconnected pieces. Continue reducing entanglement towards 0, and the 2 halves of the bulk spacetime become completely separated with infinite distance between them. Restore the entanglement, and the 2 halves reconnect, with the distance between them shrinking accordingly. Spacetime connectivity, the simple fact that different regions of space are linked to each other with finite distances, is literally created by quantum entanglement. Remove the entanglement and space disintegrates. Restore the entanglement, and space is stitched back together. Distance is not a property that space possesses independently. Distance is a manifestation of quantum entanglement among the degrees of freedom that constitute space itself. This insight has given rise to one of the most exciting recent developments in theoretical physics. The ER equals EPR conjecture, proposed by Juan Meldacena and Leonard Susskind. Einstein-Rosen bridges, which are wormholes connecting two distant regions of spacetime, are named after Einstein and Rosen, who first described them mathematically. Einstein-Podolsky-Rosen pairs, which are maximally entangled quantum particles, are named after the famous 1935 paper by Einstein, Podolsky, and Rosen. The conjecture asserts that ER equals EPR, meaning that an Einstein-Rosen bridge connecting two black holes is physically identical to EPR entanglement between those same black holes. A wormhole linking two distant regions of space is equivalent to maximum quantum entanglement between those regions. The geometric connection through a wormhole and the quantum mechanical connection through entanglement are the same phenomenon described in two different languages. What does this imply? It means that entangled particles are connected by a kind of quantum wormhole, a geometric bridge through spacetime created by their entanglement. Two particles that appear to be spatially distant because the quantum bridge between them is invisible to ordinary observation are actually geometrically connected through that bridge. The distance between them is an illusion produced by examining the wrong level of description. Our ordinary conception of distance, the kind you measure with a ruler or a laser rangefinder, is the large-scale emergent description. Underneath it, at the quantum level, the actual structure is entanglement. Two entangled particles are not distant from each other in any fundamental sense. They are connected. Distance is a macroscopic illusion that materializes when you average over quantum details. Loop quantum gravity offers yet another perspective on why distance is not fundamental. In loop quantum gravity, spacetime is not smooth and continuous at small scales. Instead, it is composed of discrete quantum units, tiny chunks of space called spin networks. The nodes of a spin network represent quanta of volume. The links between nodes represent quanta of area. Distances in loop quantum gravity are not continuous quantities. They are discrete and quantized, arriving in minimum units related to the Planck length, which is approximately 10 to the power of -35 meters. Below the Planck length, the concept of distance does not merely become unmeasurable. It becomes meaningless. There is no physical fact about whether two things are separated by less than a Planck length, because spatial separation below this threshold is not a coherent concept. Space is not infinitely divisible. It has a smallest possible unit, and below that unit the very idea of distance dissolves entirely. This means that our smooth, continuous space with its infinitely precise distances is an approximation, one that works remarkably well at scales far larger than the Planck length, but one that does not reflect fundamental reality. Fundamental reality is a discrete quantum network in which classical distance emerges as a large-scale statistical property of the network, much the way temperature emerges from the average motion of molecules even though no individual molecule possesses a temperature. Distance in space is therefore illusory in a double sense. At the quantum gravity scale, space is discrete and distance loses its classical meaning entirely. At larger scales, distance emerges as an approximate description of the underlying quantum network structure. But this emergence means distance is not fundamental. It is derived. The implications of all this are staggering. Two galaxies that appear to be separated by millions of light-years might be connected through quantum entanglement in ways that render that spatial distance physically irrelevant for quantum processes. The apparently vast separations between stars might be, at the quantum level, descriptions of entanglement structures rather than fundamental voids in space. The universe that seems to extend across billions of light-years might be, at its deepest level, a quantum system in which what matters is not spatial geometry but quantum connectivity. This does not mean you can instantly transport yourself across the galaxy by exploiting quantum entanglement. Entanglement does not permit faster-than-light communication or the transfer of matter. The quantum connection between entangled particles does not produce a traversable tunnel for information or energy. Distance may be illusory at the fundamental level, but the constraints on what can physically occur between distant regions remain firmly in place. You cannot exploit the underlying quantum connectivity to circumvent causality. But it does mean that our entire picture of the cosmos as a vast expanse of empty space with objects scattered across it at enormous separations is fundamentally misleading. The universe is not primarily a spatial structure. It is primarily a quantum structure. The spatial distances we observe are a macroscopic emergent description of the quantum entanglement architecture of reality. Consider what this means for how you experience the night sky. When you gaze upward and see stars at distances of hundreds or thousands of light years, you are not perceiving fundamental spatial separations. You are observing the large-scale average of a quantum entanglement network. The apparent distances are real as macroscopic descriptions, but they are not the bottom layer of reality. When you contemplate the Andromeda Galaxy and the 2.5 million light-year gap separating us from it, remember that this distance is frame-dependent, observer-dependent, definition-dependent, and ultimately emergent from quantum entanglement structures that do not themselves speak the language of spatial separation. When cosmologists measure the scale of the observable universe at 93 billion light-years and describe it as unimaginably vast, remember that this vastness is expressed in the approximate language of classical geometry. In the underlying quantum description, there are number 93 billion light-years. There are quantum states and their entanglement patterns, and the geometry, including all those distances, emerges from those patterns. Distance in space is real in the same sense that temperature is real. You can measure it, you can perceive it, you can build technology that depends on it. But it is not fundamental the way quantum states are fundamental. It is an emergent, approximate, observer-dependent description of something deeper that contains no distances at all. The universe is not a collection of objects scattered across an immense space. The universe is a quantum system, and what we call space, with all its distances and geometries, is simply how that quantum system appears when observed from within by a macroscopic being. When you are a large-scale creature composed of trillions of atoms interacting at energies far above the quantum gravity threshold, you are not separated from the stars by light years. You are connected to them through a web of quantum entanglement whose large-scale description we happen to call space. Every particle in your body is quantum mechanically linked to particles throughout the entire cosmos. The apparent distances between you and everything else are the macroscopic shadow of quantum connections that have no spatial description at the fundamental level. This is what distance in space truly is. Not a fundamental property of reality. Not an absolute fact about how far apart things are. But an emergent, approximate, observer-dependent description of quantum entanglement architecture. A useful fiction that we mistake for fundamental reality because we are far too large to perceive the quantum structure beneath it. The universe is not vast. The universe is quantum. And in the quantum description, there are no distances.